optimal threshold, and remember my assumption that probability 0 and probability 1 were equal. So what's the optimal Z in this case?
0.
It is
S0 plus S1.
1/2 S0 plus S1. So just remember, they're equally probable. It's halfway between S0 and S1. So this is equal to, I'm going to keep S0 because it's a complicated expression, but S1 I know is just alpha S0. So I get 1/2 S0 plus alpha S0, which is equal to 1 plus alpha over 2 S0. Okay, now we're pretty much ready to go. So the probability of error, remember the expression I had from probably 3 or 4 classes ago, is 1/2 curve C, S0 minus Z over root 2 sigma squared, that's the probability of 0, plus 1/2 curve C, Z minus S1 divided by 2 root 2 sigma squared, probability of 1. And remember the interpretation here, this is the probability of error given that a 0 was sent. This is the probability of error given that 1 was sent, so we marginalize it for both 0 and 1. Okay, the first thing we can do, by assumption, these guys are equal and both equal to 1/2. So I get 1/4 for CS0 minus Z over 2 sigma squared plus 1/4 for C Z minus S1 over root 2 sigma squared. Okay, now let's start substituting. We write that Z is equal to 1 plus alpha over 2 S0. So now, up top here, I have all of the expressions that I need to substitute into here. So probability of error is equal to 1/4 versus C. I'll keep S0 the way it is. I don't want to substitute in that sum. So S0 minus Z is 1 minus alpha over 2 S0. And I will keep sigma squared the way it is. Question?
1 plus alpha, 1 plus alpha.
Correct, 1 plus alpha. Divided by root 2 sigma squared. Plus 1/4. C 1 plus alpha over 2 S0 minus S1, which is alpha S0 divided by root 2 sigma squared. Okay, so now we basically eliminated S1 and Z, but we've added alpha. But alpha is given, so that doesn't really matter. Okay, what's this guy? So we have S0 minus 1 plus alpha over 2 S0. So I can take the S0s out and I get 1 minus 1 plus alpha over 2 S0. So that's 1 minus 1 plus alpha over 2 S0. I'm going to ignore the denominator. And that I can reduce to 2 minus 1 minus alpha, taking that minus inside that fraction. So 2 over 2 minus 1 plus alpha over 2. That's 0, which is equal to 1 minus alpha over 2. guy, I can take that alpha inside. So we get 1 plus alpha over 2 minus alpha. That's 0, just in the numerator, which is equal to 1 plus alpha minus 2 alpha over 2. That's 0, which is 1 minus alpha over 2. That's 0. So in fact, both the expressions under these RFCs end up being the same, which shouldn't be a surprise. We saw that a lot when we picked the optimal thresholds, is that with equiprobable bits, because the threshold is exactly halfway between the two, noise-free means, the symmetry of the Gaussian means that these two error expressions should be the same. So we end up with 1/4 RC of blah plus 1/4 RC of blah, where both of the things in brackets are the same, so that's 1/2 RC. 1 minus alpha, that's 0, over 2 sigma squared. Okay, so this is what we need to play with. I should have erased that. Okay, S 0 is the sum over I, 0I, each hat I, and sigma squared is the sum over I, N0 over 2PS, sum over I, each hat of I squared. Okay, so this is the expression. Probability of error is 1/2 C. 1 minus alpha, that's 0, over 2 sigma squared. And the design problem is this. Find H hat of I, or equivalently H by, minimizing the error, i.e. satisfying min over all H hat I, 1/2 ERF C, 1 minus alpha, that's 0, divided by 2 sigma squared. Okay, what I want to do is I want to find, I don't really care what the minimum probability of error is. What I care more about is what is the value of H that does that. And I'm going to use the notation arg, which is short for arguments. In other words, find the argument minimizing over H. In other words, find the H that minimizes this expression. What I'm going to call that is I'm going to call it H hat star of I. So once again, this notation means find the H that minimizes this and then return. So if I eliminated that, it would be find the minimum possible value of this probability of error. But adding the arg means find this thing that minimizes that. Using arg means that I can simplify this problem in a lot of ways that I'm about to describe.